Hi there! In this video, we will give some examples on judging true-false statements. There are three parts to this. First off, we have to understand these statements correctly. This is not always as easy as it sounds, and it will be the main focus of this video. Then we have to judge whether the statement is true or false. And finally, we have to prove that our judgment is correct. If we don't succeed in this final step, we may have to go back to the previous steps. Did we really understand the statement correctly? And was our judgment of the statement correct? Let's get started with a real-life example. After that, we will take a look at a statement in linear algebra. Consider the following statement. Christmas, December 25th, will be a Saturday, Sunday, Monday or Tuesday, whenever the December month has 5 Fridays in it. This statement can be written in the form if A, then B. What is statement A? This is not correct. It can indeed be confusing. An implication A implies B is not always written in such a way that the A statement comes first in the sentence. Can you spot a word similar to if in the question and try again? This is not correct. We are indeed talking about a December month, but the statement can be worded as if something happens in a December month, then something else will happen as well. Could you try again? This is correct. Don't be fooled by the order in which the two parts appear in the sentence. Now, can you tell what statement B is? This is correct. This is not correct. The A statement already made clear that we are talking about a December month. The statement can indeed be rephrased as if a December month has 5 Fridays in it, then Christmas in that month will be a Saturday, Sunday, Monday or Tuesday. If you want to think for yourself whether the statement is true or not, you should pause the video now. This statement is true. How would a proof start? This is correct. When you are proving an implication of the form if A, then B, you can start by assuming A. If you can then show that B follows logically, your proof is ready. This is not correct. You need to show that A implies B. If you then assume B already, your proof is not going anywhere. Let us construct a proof. If December should have 5 Fridays, we first should start with all possible options. First, consider that December 1st is a Monday. Then you get the following calendar for December. As you can see, this is not a December with 5 Fridays. So next, consider December 1st is a Tuesday. Nope, only 4 Fridays again. What if the 1st is a Wednesday? Aha, here we get 5 Fridays. The same is true if December 1st is a Thursday or a Friday. If it is a Saturday or a Sunday, we again get only 4 Fridays. So, finally, we have found 3 possibilities for Decembers with 5 Fridays. Now, Christmas is always on December 25th, so let us mark that day in these 3 calendars. As you can see, we get that if December has 5 Fridays, Christmas falls on Saturday, Sunday or Monday. Notice that the B statement also allows Christmas to be a Tuesday. However, this has no influence on our implication being true. However, it would mean that the reverse statement would be false, as you can see on this calendar. We will soon see how to show that a certain statement is false, and you will be able to use those techniques on this false statement. Let's now take a look at a more mathematical statement. Any linear system which has two different solutions has infinitely many solutions. This statement about linear systems is of the form if A, then B. What is statement A? Indeed, this is correct. This is not correct. Again, the word if does not appear in the statement, yet there is a different keyword. Can you find it? Again, the word if does not appear in the statement, but there is the word any. So the original statement can be read as any linear system for which one thing is valid also has another property. Written as an implication, we get if a linear system has two different solutions, then it has infinitely many solutions. Again, feel free to pause the video if you want to think about whether this statement is true or not, and also how you would proceed to show that your idea is correct. This statement is true. How would a proof start? This is correct. The statement is of the form if A, then B. So you start by assuming A. Since this A is about a linear system, it makes sense to give it a name. Calling it AX equals B is not a problem. No, this is not correct. The statement is an implication. You can actually see this as a challenge. If I know that a linear system has two different solutions, can I then show that it has infinitely many solutions? Then you cannot just assume that there are infinitely many solutions, because that is what you want to show. You could finish the proof as follows. Call the two solutions that we assume exist x1 and x2. Since ax1 equals b and ax2 equals b, we have by linearity that a times the difference equals 0. Hence, also a times k times the difference equals 0 for any real k. And then, still by linearity, a times this vector is b for any real k, which means that the linear system has infinitely many solutions. Alright, let's go back to a real-life example. Consider the following statement. If your team doesn't score the final goal of a soccer game, your team cannot win this game. This statement is of the form if A, then B. What is statement A? This is not correct. The statement is already written in the form if A, then B. However, you might think that it is allowed to replace the your team doesn't score the final goal by the opponents score the final goal. But then you are forgetting about the situation where the game ends in a goalless draw, in which neither of the teams score the final goal. So those two sentences are not equivalent. Can you try again? This is correct. Since the statement was already written in this way, it is fairly obvious what the statements A and B are. This is not correct. The fact that your team does not win a soccer game is exactly what the statement claims to be true. So it is the result of the implication. It is the B statement in if A, then B. Can you try again? So we have seen that this statement takes the classical form of an implication. This statement is false. How could you prove this? This is not correct. The fact that a statement if A then B is false does not mean that if A then not B is true. It is possible that if A holds, sometimes B will hold and sometimes B will not hold. If we can find one example in which A holds but B does not hold, this is sufficient to show that the implication if A then B is false. This is what we call a counterexample. This is correct. If you can find one example in which A holds but B does not hold, this is sufficient to show that the implication if A then B is false. This is the core idea of looking for counterexamples. Now let us find such a counterexample. What would a correct counterexample be? This is not correct. we want to have a situation where the A statement is true and the B statement is not. Try to see where this counterexample goes wrong and try again. This is not correct. We want to have a situation where the A statement is true and the B statement is not. Try to see where this counterexample goes wrong and try again. This is not correct. We want to have a situation where the A statement is true and the B statement is not. Try to see where this counterexample goes wrong and try again. This is not correct. We want to have a situation where the A statement is true and the B statement is not. Try to see where this counterexample goes wrong and try again. This is correct. Indeed, we want a situation in which the A statement is true, so your team does not score the final goal of a soccer game, and this was not true in the third and fourth option. But also we need B to be not true, so we want a situation in which your team did win the game, and this went wrong in the first, second and third option. The fifth option was the only one in which your team didn't score the final goal of the game, and yet they won. As a final example, let's go back to linear algebra. Take a good look at the following statement. This statement can be written in the form if A, then B. What is statement A? Indeed, this is correct. This is not correct. It is actually the B part of the statement. It is the consequence that is true according to the statement if we have some other condition A. The word if does not appear in the statement, but the word any tells us what the statement is all about. It says that if a set v1, v2, v3 in R4 is linearly dependent, then this set contains a zero vector. Again, feel free to pause the video and decide whether this statement is true. This statement is false. You can show this by giving a counterexample. Now, what would you look for in a concrete counterexample? This is not correct. The statement claims that something happens for a linearly dependent set. So any statement concerning a linearly independent set does not teach us anything about the validity of the statement. Could you try again? This is not correct. The statement claims that something happens for a linearly dependent set. So any statement concerning a linearly independent set does not teach us anything about the validity of the statement. Could you try again? This is not correct. It would be an example of a situation where A and B are both true. Notice, by the way, that this would also not give a proof for the statement being true. An example can never show that a statement is true in general. Could you try again? Indeed, if we can find a set with those conditions, we have a correct counterexample. It will be a linearly dependent set that does not contain the zero vector, which is in contradiction with the statement. Finally, which of the following is a correct counterexample? This is correct. The set does not contain the zero vector. Moreover, it is linearly dependent. Now, remember, you should show this. Here it is pretty obvious, since the first and second vector add up to the zero vector. Do you also see why the other options were not correct? This is not correct. The set is indeed linearly dependent. However, it contains a zero vector. Could you try again? This is not correct. The set does not contain the zero vector, which is good. However, these vectors are not linearly dependent. Could you try again? This was our final example. You can easily train yourself. Take your linear algebra book or go to Graspel. Take a look and see if you can read those statements as implication. Let's see. Exercise 1.4.23c. The equation ax equals b is consistent if the augmented matrix has a pivot position in every row. Try to imagine what you would need to do to show that this is true. How would a correct proof start? Or maybe, is this statement wrong? In that case, what would you look for in a counterexample? Good luck and see you in class!